from group M7C. Today I want to explain about working principle of Geiger molecule. Basically, Geiger molecule is a device that used for detection and measurement of all types of alpha, beta and gamma radiation. It consists of a pair of electrodes surrounded by a gas. Usually the gas is helium and argon. So as the radiation enter the tube, it can ionize the gas. The ions will attracted to the electrode and electric current will produce. A scalar will count the current pulses and it will obtain a count whenever the radiation ionizes the gas. There are a few important things that we need to take note in this Geiger molecule. The first one is low applied voltage. So at a very low voltage, the count rate is insignificant. The tube generally cannot operate usefully in this region. The second one is starting voltage. The starting voltage Vs is defined as the lowest voltage applied to a counter tube at which pulse can be detected. The third one is threshold voltage. Above the starting voltage, the count rate increases rapidly, so the voltage will further increase to reach the threshold voltage Vt. The fourth one is plateau. The threshold voltage also marks the beginning of the GM tube plateau for the condition under which circuit is operating. So as the past the threshold, further increased voltage result in negligible increase of counting rate. This region is called the plateau, and operating voltage VO is selected within this plateau. So the last one is discharge region. If the voltage is increased further past the plateau, then another rapid rise in the count rate takes place. This region is called the discharge region. In this case, the voltage is large enough to cause the atom to self-ionize. So all of the things I mentioned earlier can be found in the characteristic curve of a Geiger molecule. So now I will explain the procedure of the experiment A. So basically, experiment A is being carried out in order to study the characteristic curve and determine the operating voltage for a Geiger molecule. So first of all, we need to switch on the Geiger molecule first and then wait for the counter to warm up for a few minutes. Then we place the radioactive source onto the placeholder by using this tool. So we need to take this and then place it on the sample holder. Make sure that the green side is placed upward so that the GM molecule can detect the radiation. So the important thing that we need to take note is that this sample holder, the plate needs to be fixed throughout the experiment. So and then we set the time to 30 seconds. And then we must make sure the rate is always 0. And for the voltage, usually Geiger molecule can detect minimum of 400 volt and above. So for example, I will put it at 700 for example. So 700. So and then we select the count and we press the count and wait it for 30 seconds. And after 30 seconds, the light at the stop will light up. So we get 327 count. So this is not the starting voltage that we need, that we want. So we must set the voltage. We reduce it by 20. So we count again. So if we get the value of 0 at that count, so that is our starting voltage. So as the starting voltage we can start to record the count rate. We can increase the interval by 20. For example, I get the starting voltage at 680 volts, so I will increase it by 20, so 700, 720. And at some point the rate should remain fairly constant over a range of applied voltage, and then it will increase rapidly as the applied voltage is further raised, which that indicate that the tube is entering the breakdown region. So we observe the data. If the rate is fairly constant, so that is the beginning of the threshold voltage or plateau, and then at some point it will increase rapidly, so that indicate that it has entered the breakdown region. So we need to limit the applied voltage to 1200 volt, and we can obtain the breakdown voltage and the corresponding count rate. After that, we can plot the graph of rate versus the applied voltage, and from that graph we can find the operating voltage of this Geiger-Müller tube. So now I will explain what I understand from the experiment A. So basically, if we have get the data, we can plot the graph, and then this is an example of the characteristic curve of a Geiger-Müller tube graph. So we can find the operating voltage by dividing the threshold voltage and the breakdown voltage at this, and we add these two and divided by 2, and we obtain the operating voltage for this Geiger-Müller tube. So basically, operating voltage is a maximum voltage that a Geiger-Müller tube can measure.
For experiment B, the objective of experiment B is to show the standard deviation for a single measurement R can be estimated as surd R over T with 68%. Basically, experiment B is for to confirm does the surd R over T lies at the 68% confidence by using the same voltage but with multiple times of measurement. We use the constant voltage, that is voltage operating, the operating voltage VOP that we get from experiment A, 840 voltage. So firstly, we set the operating voltage as applied voltage here as 840, and then the time for 30 seconds. Okay. After that, we take the count. Okay, for the data and analysis part of the experiment B, we have to construct a table of reading, counting rate, and the standard deviation. After we construct this table, we have to do some calculation to find the range or to find the standard deviation. After we have the standard deviation, we must calculate the error of the standard deviation, the plus and minus, and then the value between the. We have to find the number of data for this range. For example, the range is between 6.7 and the 6.323, and then the number of data that have the range of the number, we divided by 20 because the measurement is 20 readings, and multiply with 100% to find the percentage of confidence. After that, we can construct the bell curve to identify the region of the standard deviation, whether is it between the 68% confidence or not. Okay, next for the experiment C, the objective is to determine the range of beta radiation. We use the same beta radiation, but we just add the aluminium foil. Different thickness of aluminium foils. Firstly, we can see this, the aluminium foil thickness, and this. You can see the different thickness, right? Okay. With the different thickness here, we put it at the stage. This is the radioactive and the aluminium, and then we set the voltage at the operating voltage, and the time still 30 seconds, and then we start to count until the light turn to the button of stop. The objective of this experiment is to know whether which aluminium thickness that can still get the radiation of the beta ray. Okay, here is the data and analysis for the experiment C part 1, the background counting rate for without the absorber. We have to find the background radiation rate without the absorber, without the aluminium. So we have to construct this table and then do the calculation part to find the background radiation rate and the error. After that, we make another table for data and analysis part 2 with different thickness of absorber. We can see the thickness is from 129 until 849. After we got the counting rate, we have to find the lone R, and then we plot a graph of counting rate and versus the thickness. Another graph of logarithmic of counting rate lone R versus the thickness. And then we have to plot or make a straight line to find the gradient. The gradient will indicate the absorption of coefficient beta particle. After we do some calculation, we can get the extrapolated range of beta particle, the half thickness, and the beta absorption coefficient. This is the counter. This is the what? Oh, it's the back camera. Aku tengok je. Yalah.